Good afternoon, everybody. My name is Samuel REQUILE. I'm head of composite process and performance at Coriolis Composites and leading the thermoplastic roadmap. And I'm happy to share the stage today with Alexandre from Daher Aerospace.
Hi, everyone. I'm Alexandre from Daher. I'm a design engineer, and I'm working as a R&D project manager for Daher. So thank you, Sam, for the invitation today.
If you can have the slides up, that would be great. Oh, if it's us. All right. So we're going to be talking about thermoplastic automated fiber placement for large and complex aerostructural parts. And we're just going to start by a quick introduction of both of our companies. So Coriolis Composites is part of a larger group, which is Coriolis Group, with on one side, so two main technologies. On one side, filament winding with MF Tech company, and on the other side, automated fiber placement with Coriolis company. So what's AFP? It's what you see here. So basically what we want to do is we want to fit in some space within some boundaries, within the part contours, by adding plies on top of each other to have a full stacking and manufacture a part. And we can be using different kind of materials, basically pre-preg tapes, so using dry fiber, using thermoset fiber or thermoplastic fiber. And the specificity of thermoplastic fiber, because it's the main topic of today, is that we need to reach process temperature that are higher than the melting temperature of the different materials that can be above 350 degrees or 450 degrees. And it's just to be understood that the main benefit of automated fiber placement is to switch from quasi-isotropic parts to anisotropic parts and do steering capabilities to localize and to be able to place the material exactly where it's needed and with fiber orientation that corresponds exactly to the stress requirements. So we have four main activities. The first one, of course, machine equipment. So we develop, produce, and commercialize fully equipped robotic cells equipped with different technologies. So we're talking about AFP, filament winding machines, or additive manufacturing machines, which are really flexible, meaning that they can adapt to different structures, different geometries, or different scales, and some different technologies or products can be plugged and unplugged from these machines. In-house value-added software development, so we have three main softwares that are machine-independent and that enable to do the simulation of the process and to support these products, of course, customer support capabilities and composite engineering to allow all our customers to have a complete project workflow from the feasibility studies to full-scale demonstrator, for example. So what we want is to have a network of expertise in composites to be able to meet our customers' challenges and to develop new solutions. So we have a bit more than 100 automated fiber placement machines around the world in different domains of activities with a strong track record in the aerospace industry, of course. And you see a large panel of our customers here, from which Daher is part, and we'll talk about his company now.
Thanks, Sam. To start, a few words about Daher. So we are 10,500 people. We have a revenue of 1.3 billion euros in 2022, split in two between aircraft and services. We are 500 engineers, and we're recruiting more engineers, and we are split in four different activities. So we are aircraft manufacturer for the TBM and the Kodiak airplane. We manufacturing part for other aircraft manufacturer, and we as well providing manufacturing services and logistics. We are developed in 13 different countries. Mainly we are in Europe, but we are growing in North America. To grow, they are pushing on innovation. So they have built 3 new technical centers. One for aircraft, one for industry, and one for logistics and services. For the part we're going to develop and speak about today, we develop all those parts in shaping. So shaping is based in Nantes, in France. And at shaping, we've got the thermoplastic AFP machine we use to develop those parts. So to start with a bit of context, I will explain the 3 main challenges we've got for the growth of TP composite. So of course, the first and the biggest one is environmental sustainability for future aviation. So for that, we all know that we need recyclable material. So thermoplastic is one of the solutions for this topic. Second big change is the weight and cost saving that we need to have for highly loaded structure. So for that, we need good performances material. And that's why at Daher we focus on unidirectional fiber. And the third one is to meet the high rate capability, high rate production that our customer demand. And for that, we're focusing as well on automated processes. And to combine all of that, we need like a robotic, automated processes able to lade thermoplastic unidirectional fiber, and AFP is one of the solutions that provide that.
And we've been thinking of what can drive the future growth of thermoplastic, and well, similarly, it's about continued evolution of manufacturing processes. So you have on one side people doing research and development around how can we do VBO, can we weld, can we assemble, and also disruptive technologies like automated fiber placement technology, in situ consolidation using the AFP, or continuous fiber additive manufacturing, for example. So it's how can we really disrupt the paradigm of making materials. And it's not too different from the growth of thermoset materials, where ultimately they materialized and they grew when people figured out how to better use them. Not to be undermined, of course, we need more platforms needing thermoplastic composites. So we're talking about future high-rate commercial aircraft that need an increase in the manufacturing rate. And also UAM, UAVs, or automated transport. All those need more thermoplastic composites and show the potential to produce more composite parts a day. And one key to succeed, and not to be forgotten, is that we need the acceptance from the industry and from all of us that thermoplastic is not the only material, but we need to have to make the right choice of the material to make a part, to be able to be at most cost-effective, energy efficient, and as lightweight as possible. So to integrate thermoplastic to replace thermoset composites is not only a story of changing material or changing the process, but is to be taken into account as early as possible in the process chain and from the design phase, as it must be adapted to the manufacturing processes. So here, automated fiber placement, and to all the different materials like thermoplastic materials. So now that we've set the topic, we're going to show you a bit more concretely what we're doing in both of our companies and how we work together. So at Coriolis Composites, we have different collaborations, so industrial collaborations, research and development collaboration with some labs or some tech centers around the world, around three main thematics in terms of R&D programs. So of course, machine development. We consider that the machine reached a TRL 9 in terms of thermoplastic processing, digitalization, and material understanding and all the different phenomena that occur during the process, and we're going to talk about that a bit later on. So you see just a quick graph here with the different AFP machines that are around the world on a 100% basis, and the increase of the thermoplastic AFP machines that are dedicated really on a client side for thermoplastic processing, with an increase in the last few years. Just to show you what we've been doing, we started working on thermoplastic 10, 15 years ago by doing simple 2D parts, going thicker and thicker. Started to do some 3D parts, some corner parts with all the advantages and the challenges that we will talk about. And then finally today, we have complex structures, 3D structures with double curvature, with some localization of the material and the functionalization like you see on the right-hand side.
At Daher, we focused on different part and family. So we using thermoplastic and AFP on torsion box welding, engine part, wing part, and we're using the benefits of thermoplastic by developing R&D projects for recycling as well. What's important to say is all our R&D topics are driven by a certification approach. So it's important for Daher to provide to the customer a solution from the design to the end manufacturing, and make sure this part or this technology is flyable. So to start with, this is a few use cases. So I would like to speak about the 3D AFP and the consolidation. So why we use 3D AFP at Daher is to be able to lay complex and various shapes for layup and in a relatively fast way. So as you can see on the two pictures, we've got completely different parts. So we can have some U shape like that, 1 meter long part and 35 millimeter thick parts, and a completely different parts like way longer, 3 meter long, thin parts, so 2.5 millimeter. So the AFP is very good to lay like very complex and various shapes. But to do that, we've got some different challenging. So laser management, machine kinematics, and process control and monitoring. So Sam's gonna discuss a lot about that after. And for this one, and for this part especially, I think the most important is to focus on the heat homogeneity between all those parts.
So as a machine manufacturer, we have two main goals. The first one is to understand the process parameters that are related to different topics. The first one are the optic parameters. As I said, for thermoplastic, we're using a laser optic system to heat the material. So here we're talking about the optic type, the laser beam shape, the laser spot dimension and position on the material, if it's on the incoming fiber, on the substrate, and so on. And also, added to this, we need to have information on the laser-matter interaction, which is more linked to the material itself. So we're talking about rugosity, fiber volume fraction, fiber impregnation quality, and so on. The main goal here is to understand the different phenomena and the different material behavior that occur during the three phases of the process, as you can see here. So the heating phase, the consolidation phase, and the release phase. We have all different kinds of phenomena that occur in a few milliseconds. And this knowledge will bring us information of what temperature we need to fix for the process and for the material to reach. Once we have this temperature, our second goal is to make sure that this temperature stays constant during the whole process to have part homogeneity and to reduce the effect of generation of stress gradients, of thermal gradients, and to make sure that we can guarantee the repeatability of the part and that we can make 100 parts the same way. So to do so, and to reach this part homogeneity, the building block is the laser heating simulation block in Sibereal software, sorry. Basically, in quick words, what we want to do is we want to simulate the energy distribution on the part before doing the layup, so during the simulation. So what you see here is a heat homogeneity estimation that we want to estimate, we want to control it. And this is an example of a part that is manufacturing. And we had the feedback from the customers that there was some region with some defects and some surface defects. So by running all this in the simulation, what we saw is that we had some critical region in terms of heat management. So with overheated regions on the corners you see in red, and some regions where temperature was not high enough, so the cool region here. So these bring heterogeneity in the part. And basically, by optimizing the process parameters inside the software, so again, before the layup, and by tuning the heating loss, so by choosing the right laser power for a specific speed and for a specific position on the part, we were able to reach a good part homogeneity and to optimize the quality and the performances of this part. So Coriolis has developed these two building blocks to meet the challenges exposed by Alexandre, Daher, and other customers. Here, so it's the temperature homogeneity that is one of the main drivers, again, of part quality and performance, and to reduce the cost due to non-quality.
So now I will discuss about like a second way of using AFP. So we spoke about the 3D layup. So now I will speak about the 2D layup with direct stamping associated. So direct stamping is a patented technology by Daher. So it's forming and consolidating the parts in the same time just after the AFP process. Why we use direct stamping? So it's a very fast process, so we can meet the high rate capability requested by a customer. we can have tailored blank that with the AFP machine. So that's allows us to optimize the buy-to-fly ratio, which is important for us. And what's very important and what we're focusing on is having this technology with the same level of performance than we have for the standard consolidation process. What I forgot is to say that the direct stamping technology is only applicable with AFP processes because it demands a level of laser power, very precise. So we developed that at Daher. So we use this kind of technology for wing rib application mainly. So those are different ribs we did for Wing of Tomorrow program for airplane like A320, A350, or business jet rib as well. We can do that. If you want to look at the part I spoke about today, you're free to join at the Daher booth. They are all physically there, so feel free to come if you want more details. And to manufacture those parts, especially, we've got similar challenge for the 3D AFP, but in addition there, we will look at where the gap are, where the splice are, and where are the fiber orientation to make sure we've got all as it is designed by Daher. Sorry.
So again, that's another building block proposed by Coriolis, basically to reach the high rate capability and to reduce the buy-to-fly ratio. We focused on reducing the inspection time by developing an automated inspection system. So it's the little blue box that you see behind the head here. So we have a detection software that enables to detect different defects of the part. What I mean defects, it can be foreign objects, it can be all the gaps, the different overlaps, and to make sure that they are in the specifications or outside the specification if you need to repair. And associated to this detection software, we have an analysis and visualization software to be able to quantify these defects, basically their dimension and their position on the ply and within the plies, and see again if repairing is needed. And if repairing is needed, we can associate this technology with laser projection for fast repair of the operators. Two other building blocks about monitoring and possible certification of the process are high-frequency data monitoring and visualization. So what we want to do is to store the different process parameters, meaning the temperature, the layup speed, the compaction pressure, for example. And we want to store that and specialize the data in the parts coordinate system and to have a mapping of all these different process parameters on the part. Second one is the heat control. We talked about the temperature that needs to be controlled and the homogeneity of the temperature in the part. Here, it's a closed-loop system, so basically it's an autonomous control of the laser power. I was talking about the fact that we create heating laws, so specific laser power depending on the speed. Here, the idea for the operator is to fix only a temperature on the HMI, and we have an autonomous closed-loop system that will adjust the laser power depending, again, on the speed, on the different material factors, and so on. So finally, and for a quick conclusion, Coriolis planned to address thermoplastic challenges that were exposed by Alexandre, by Daher, and some other customers. For that, we are developing different building blocks, I was saying, through R&D projects on machine development, process development, digitalization, through different R&D thematics. So invent products. I'll show you some different building blocks today. Increase the reliability of the process itself, and increase the knowledge in terms of process parameters, of how to tune the process parameters, and in terms of material behavior that is quite complex and more complex in thermoplastic processing. And the main goal for us is to push forward, of course, the automation, so automated fiber placement, and also the thermoplastic material, not just because it's a trend, but because we want to take most of the advantage and the benefits of this material using our technology and with Daher. So thanks a lot for your attention. If you have any questions, I think we have a bit of time to answer some questions. And please feel free to meet us on both D35 and C32 to see the nice parts and have more information. Thank you.
Nothing to add. Thank you very much. Thank you, the fan club.
Yeah, I don't know if there's a microphone somewhere or if you can speak loud.
Hello? Okay. How much does the speed of the, when you're doing the 2D AFP direct to stamp form, is speed a factor on the AFP itself to get the right consolidation level to go into the stamp forming?
Yeah, it's relatively fast. We can go generally up to 0.8 meter per second in 2D. Yeah.
Any other questions? All right. Thank you very much.